Imagine an attacker who doesn't target your operating system, your network, or even your applications. But instead, they manage to compromise the literal microscopic silicon on your server's motherboard before the system even wakes up.
Yeah, it's a terrifying thought.
It really is. Well, welcome to today's deep dive. If you are joining us, you're likely looking to really master the complex material for the D-PE-FN-01 exam.
Right.
And I want to set our expectations right out of the gate here. This deep dive, it is not about rote memorization or just checking boxes on a practice test. We are going to explore the rigorous architectural why behind enterprise server environments.
Exactly, the underlying logic.
Right. We will unpack how all these incredibly sophisticated pieces, from physical physics to cryptographic logic, how they all fit together to build a robust system. And to do that properly, we're going to take a very measured, deliberate pace today.
I think that's crucial.
Yeah, there is absolutely no rushing here. We want to ensure that you have the time to fully absorb, really visualize every single complex engineering and security concept we discuss.
That is definitely the right approach, because building a truly secure, highly available data center is, well, it's an immense engineering undertaking. You cannot build a secure system starting at the software layer.
No, software is too malleable.
Exactly, it's malleable. You have to start at the absolute lowest, most rigid hardware level. Before a server even begins to think about loading an operating system, it requires a foundation of absolute trust, which brings us directly to the physical hardware and seamlessly sets up our first question.
Let's get right into it then. Question 1. When designing a secure server environment, administrators often implement a silicon-based trust mechanism. What is the primary function of this embedded hardware security feature during the startup sequence?
The correct answer is A. A silicon-based root of trust establishes a secure foundation for the server boot process. It cryptographically verifies firmware components before they are executed, preventing modified or unauthorized firmware from continuing the startup sequence and loading the operating system.
Okay, let's unpack the how here, because, cryptographically verifies can sound a bit like magic if we don't break it down.
It does.
Like, I think of it as a highly strict nightclub bouncer checking IDs, right?
Yeah.
It prevents unauthorized code from even getting in line to enter the operating system.
That's a really good analogy. During the manufacturing process of the motherboard, specific cryptographic keys, essentially long mathematical strings, are permanently burned into the silicon chip using something called fuses.
Okay.
And once those microscopic fuses are blown, the data is physically immutable. It literally cannot be rewritten.
Yeah.
Yeah, so when you power the server on, this silicon chip acts first. It looks at the firmware, which is the very first piece of low-level software trying to run, and calculates a mathematical hash of that software. Then it compares that hash against the immutable key physically burned into its circuits.
So if a malicious actor has altered even a single line of that firmware code to inject malware, the resulting hash completely changes. The ID no longer matches what the bouncer has on the clipboard.
Precisely. The calculation fails. And because this logic is happening at the hardware level, the silicon simply refuses to send the electrical instruction to continue the boot process. It stops the threat before the main processors are even allowed to participate.
Which makes perfect sense.
Yeah.
But assuming the firmware is pristine and that strict verification passes, the server powers on.
Right.
And immediately, those high-density enterprise processors start drawing massive amounts of electricity, which of course converts into intense thermal energy.
A huge amount of heat, yes.
Yeah, and managing that heat brings us to our physical environment. Question 2. Modern high-density data centers increasingly adopt direct liquid cooling solutions over traditional air cooling. What underlying principle makes this approach highly effective for managing processor temperatures?
The correct answer is B. Liquids have much greater heat capacity and thermal transfer efficiency than air. Direct liquid cooling removes heat close to high-temperature components, such as CPUs and GPUs, allowing dense servers to operate efficiently while maintaining safe processor temperatures.
Let's make the physics here really relatable. It is basically the difference between reaching into a 400-degree oven, which is air, versus touching 212-degree boiling water, which is liquid.
Oh, that's a vivid way to picture it.
Right. You can put your hand in a hot oven for a second and be fine, but boiling water burns you instantly. Water absorbs and transfers thermal energy far, far more efficiently.
It does. And that works because air molecules are sparse. When you blow air across a hot metal heatsink, you are relying on scattered air molecules to bump into the metal, absorb the heat, and carry it away. That works fine for a laptop. But in a modern enterprise server rack, you might have dozens of processors packed into a space the size of a pizza box.
Yeah, air simply lacks the molecular density to absorb that sheer volume of thermal energy quickly enough.
Exactly. So if you run a microchannel of liquid directly over the CPU, the dense liquid carries away the heat magnitudes faster than fans blowing air.
It prevents the processors from physically melting down.
Right. And once you optimize those physical temperatures, you can focus on optimizing data flow, specifically how the processors access memory.
Okay, that brings us to question 3. To achieve maximum memory bandwidth on a dual processor server motherboard, how should the memory modules be distributed across the available slots?
The correct answer is C. Modern processors contain multiple independent memory channels. Populating memory symmetrically across the channels of both processors allows more channels to operate concurrently, maximizing aggregate memory bandwidth and avoiding performance limitations caused by uneven memory placement.
I always compare this to traffic management.
Okay, how so?
Well, instead of jamming all cars into a single lane, which is asymmetrical, symmetrical population opens up all the lanes on a multi-lane highway. It allows maximum traffic flow simultaneously.
That is exactly what happens electrically. Inside the CPU, the memory controller has multiple independent physical pathways, or channels. If you only put memory sticks into the first 2 slots on one side, you force the CPU to funnel all of its requests down a single congested pathway.
A massive bottleneck.
Exactly. But symmetrically placing them evenly across all channels lets the controller stripe the data. It sends data down all those separate physical channels simultaneously during the exact same clock cycle.
That is brilliant. Okay, so we have secure booting, great cooling, and fast memory. But what happens if the main operating system crashes entirely?
I will actually take this next one. Question 4. An enterprise server becomes entirely unresponsive, and the main operating system has crashed. How does the integrated remote management controller allow an administrator to recover the system?
The correct answer is D.
Right, because an integrated management controller operates independently of the server's main operating system and normally receives standby power. It provides out-of-band functions such as remote console access, hardware monitoring, power cycling, and system recovery, even when the operating system has crashed.
Wait, I need to ask a clarification question on behalf of the listener here.
Yeah.
If the OS is dead, how does it even have power to broadcast anything to an administrator?
That is the critical detail independent standby power. Inside that server is a separate system on a chip called a baseboard management controller, or BMC. And the power supply provides a dedicated standby power rail directly to it. So it's like having a secret backdoor with its own separate mini generator. As long as the server is physically plugged into the wall, that tiny BMC remains awake.
Wow, okay, so it intercepts your commands and can force a hard reboot.
Exactly. It's completely out of band. But let's shift the focus from software OS failures to physical hardware failures, specifically hard drives.
Okay, question 5. A physical drive fails in a redundant array of independent disks. After inserting a replacement drive, the storage controller begins the reconstruction process. What is the most significant operational consequence during this rebuild phase?
The correct answer is A. During a RAID rebuild, the controller must read data from the surviving drives, reconstruct the missing information, and write it to the replacement drive. These intensive I/O operations and parity calculations reduce storage performance until the rebuild is completed.
I think we really need to highlight why this matters to you, the listener. A server doesn't just magically snap back to normal when a new drive is inserted.
No, it definitely doesn't.
Right? The storage controller has to use specialized mathematical logic to deduce what was on the dead drive. The heavy lifting of that parity math is what causes the temporary system lag. The system is consuming its own compute resources to mathematically heal itself.
That's a great way to phrase it. And recovering from those hardware faults is essential. But we also need to connect that back to protecting against software threats during system startups, which we touched on earlier.
Oh, right, the boot process. Question 6. Modern servers utilize a unified extensible firmware interface rather than legacy startup systems. Which critical security capability is exclusively enabled by this modern firmware architecture?
The correct answer is B. UEFI supports secure boot, which validates the digital signatures of bootloaders, firmware drivers, and other startup components. Unauthorized or modified boot software is blocked from executing, helping protect the server against bootkits and other pre-operating system attacks.
I like to compare UEFI Secure Boot to a digital wax seal on an envelope.
A wax seal, yeah.
Yeah, it guarantees to the system that the bootloader hasn't been intercepted or modified by a bootkit before being executed. It's using public cryptographic keys to check that signature.
Exactly. If a piece of malware has infected the bootloader, it won't possess the vendor's private key. The signature won't match, and UEFI instantly halts the boot process. But while UEFI secures the boot software, we also need to secure the humans logging in to manage the system.
Humans are always the wild card.
Always.
Question 7. When configuring administrative access to a server management interface, an organization implements role-based access control. What is the fundamental architectural advantage of this security model?
The correct answer is C. Role-based access control assigns permissions according to a user's responsibilities rather than granting every user full administrative privileges. This supports the principle of least privilege and reduces the risk of accidental changes or unauthorized management operations.
Basically, this is like a real-world building analogy. It's giving an employee a key that only opens their specific supply closet, rather than handing every single employee a master skeleton key to the entire building.
That is the perfect way to look at it. If an administrator's credentials are stolen by a phishing attack, the attacker is trapped inside that narrow role. They can't burn down the whole data center.
But how do we ensure those administrators can always reach the server to actually use those permissions, even if a cable breaks?
Redundancy. Let's
Okay.
take this question. Question 8. To prevent a single cable failure from isolating a server, an administrator configures multiple physical network interfaces to act as a single logical connection. What is this network architecture strategy called?
The correct answer is D.
Right, because network interface teaming combines multiple physical network adapters into one logical interface. If one adapter or cable fails, traffic can automatically use another connection, maintaining server connectivity and eliminating that individual link as a single point of failure.
I mean, this is the ultimate IT equivalent of wearing a belt and suspenders. If one snaps, your connection doesn't drop.
Exactly. The protocol seamlessly shifts the traffic to the surviving cables in milliseconds. And once you have a highly reliable network connection, you want the data traveling across it to be as fast as possible, which brings us to modern storage protocols.
Let's get into it. Question 9. Enterprise solid-state drives using the non-volatile Memory Express protocol deliver significantly lower latency than older serial-attached interfaces.
Yeah.
What design characteristic provides this performance leap?
The correct answer is A. NVMe communicates through PCIe and supports many parallel command queues, with numerous commands in each queue. This architecture allows processors to submit and complete storage operations concurrently, greatly reducing latency compared with older serial storage protocols.
Let me visualize this for you. Older serial interfaces are like a single-file checkout line at a grocery store, everyone just waiting in one long line.
A very slow line. Very slow. But NVMe is like instantly opening thousands of self-checkout lanes side by side, processing massive amounts of data concurrently.
That is exactly it. NVMe bypasses the old middleman controllers and plugs directly into the PCIe bus.
Yeah.
It can support up to 64,000 separate queues simultaneously.
That is just incredible. But this brings us to the final, ultimate safety net. Because all this fast, secure, redundant architecture means absolutely nothing if the entire building loses power.
Without electricity, there is zero availability.
Right. Question 10. In a highly available server rack, dual power supplies are connected to separate power distribution units. To protect against a total facility blackout, what infrastructure component must supply immediate temporary electricity until backup generators activate?
The correct answer is C. An uninterruptible power supply provides immediate battery-backed electricity when utility power fails. It keeps servers and supporting equipment operating during the delay before backup generators start, preventing sudden shutdowns, service interruptions, and possible data corruption. I think this ties off beautifully with the track and field analogy. The UPS is the critical baton pass in a sprint relay.
Oh, I like that.
Yeah, it only holds the energy baton for a short burst, just long enough for the heavy backup generators to get up to speed and take over the race. It's the bridge.
We have comprehensively mapped the D-PE-FN-01 exam material from the hardware security of Silicon Trust and UEFI through the physical necessities of liquid cooling and UPS systems into the high-performance realms of memory bandwidth and NVMe, and finally through the management strategies of out-of-band access, RAID parity, RBAC, and network teaming.